So earlier we introduced a special log. We call it the natural log, which is e as the base log. Okay, we denote it as ln of x. So there's another log called a common log, which is when log use 10 as the base, and then we can just write as log of x. Okay, so if the base doesn't have any specific value and the default value is 10, we call it common log. Okay, the first one is called a natural log. So we have two special log, natural log and a common log. So now let's look at a specific example. Okay, very similar as the one we did with the natural log. So that's the graph of the common logs, okay, because it's a 10 as the base, right? So the growth factor is larger than the e. That's why the exponential form is more close to the y-axis, okay? That means data grows more faster as x increases by 1, right? And then is inverse functions graph symmetric with identity functions line, right? So that's the red color common log functions graph. And it always passing through the x-intercept 1, 0. And then the vertical asymptote is the y-axis. So now let's look at an example similar as the earlier one we did with the natural log. Find the domain of the log function f of x equals 2 times log x plus 1. So if you notice here, it doesn't have a specific base, right? So default is 10. So find the domain. It's the same requirement. It's x plus 1 need to be a non-negative number, right? So x plus 1 greater than 0. We can solve x must greater than -1. And then if we write as interval notation, that's -1 to positive infinity, right? -1 to positive infinity. And then graph this function, we can use the transformation techniques. Okay, I just sketched the graph. This is a point 1. Okay, it's a more close to x-axis. This is the graph for f of x equals log of x. And then next one we do f of x equals 2 times log of x. Okay, so that's vertically stretched by 2. Okay, that's every x coordinates, y is multiplied by 2. Okay. And then the last step is the horizontal shift, right? So last one, we graph f of x equals 2 times log of x plus 1. So replace x by x plus 1, that's horizontally shift to the left-hand side 1 unit. So this vertical line is x equals -1. All right. So now the x-intercept is at origin 0, 0. All right. So let's look at a more accurate graph. So two-step transformation. Okay, that's the initial graph. And then the book kind of skipped the vertical stretch by 2. Okay. Or you can do the horizontal shift first and then vertical stretch by 2. That's fine. But the key is the vertical asymptote is no longer y-axis anymore, right? After horizontally shifting to the left-hand side 1 unit, and then the vertical asymptote changed to the line x equals 91, which is this vertical line. Okay, right? Graph as the red dashed line. And then the x-intercept will be the origin 0, 0, right? Used to be 1, 0, now shifting to left-hand side 1 unit, that becomes 0, 0. All right, now let's back to the part C. We got A and B done, right? Part C. From the graph, determine the range and the vertical asymptote. The range is still all real numbers. Okay, that one doesn't change. So our real number we write as from negative infinity to positive infinity. And then the vertical asymptote we can see clearly from the graph is the vertical line x equals -1. Okay, that's the vertical asymptote of this function. And then the next step, we're trying to find the inverse function. Okay, so we write as y equals 2 times log x plus 1. And then first step, we swap x and y, right? X equals 2 log y plus 1. And then both sides divided by 2. So x over 2 equals log y plus 1. And then write as exponential form. Remember, this is default is a 10, right? 10 base. So 10 raised to the x over 2 power equals y plus 1. So now we can solve the y, right? Subtract 1 on both sides of the equation. So y equals 10 raised to the x over 2 power minus 1. Okay, that's the inverse function. Okay, we can write as, I don't have a space. Okay, I write on the top. Inverse function of x, that's equals 10 raised to the x over 2 power minus 1. So we got a D done. And then find the domain and the range of the inverse function. Domain of the inverse function is the range of original. Okay, so inverse function domain, that's original function's range, right, which is negative infinity to positive infinity. All right, this is and the inverse function's range, that's x greater than -1, right? That's from -1 to positive infinity. All right, that's the domain and range of inverse function. And then graph the inverse function, we use the inverse function's graph symmetric with respect to the identity function's graph. Okay, so let's look at a more accurate graph. All right, so the red color one, that's the inverse function's graph. Right, original function, the log function is in the blue color, okay? And then this black color line is identity function's graph. So the red color graph we got is from the symmetrical property, okay, with xy swapped. So you pick up several points from the original function's graph and then switch x and y, and then you will see. Okay, this is -9 over 10, -2. In the inverse function, corresponding point will be -2, -9 over 10. Okay, and they're both passing through the same x-intercept, which is origin 0, 0. All right, that's how we get the inverse function's graph. Is based on the symmetrical property with respect to identity function.